I gave her help. Good evening, everybody. It's a SCI sponsored talk tonight, so thank you to our sponsors from the SCI. We have here Dr. Jon-Paul Griffiths, who studied his PhD at Nottingham-Trent and then did his postdoctoral associate at Oxford. Since 2006, he's been the founder and CTO of CPS-SCI that works in surfaces and carbon chemistry predominantly, pretty much. And he is a fellow of the SCI and has won the Young Industrial Prize in 2010. So many years of experience and a good talk ahead of us tonight. And again, thank you for Dr. Jon-Paul coming in tonight, and thank you once again to the SCI.
Brilliant. Well, sorry, let me just grab some water. It's great to see you all tonight, and hopefully I will keep you entertained. What I will do is go through pretty much the last 20 years of my life and give you a bit of a breakdown about how I got to where I am today, the trials of setting up a spin-out company and trying to commercialize university research, and just a lot of other random things that came into my head as I was putting this presentation together. But yeah, great introduction. I'm Jon-Paul. I did my PhD in organic superconductors. I'm an organic chemist by background and training. I've been thrust into the world of materials and surfaces and interfaces for about the last 20 years. Really interesting for a chemist to be in that position. It's really interdisciplinary. I have to work with pretty much all the customers I deal with are engineers. It's had to change the way that I think about chemistry and how I communicate it with people. And hopefully some of that will come across here. And you'll see really where chemistry can get you. Outside of pharma and other things, there's loads of places that chemistry is used, and I shall touch on some of the really interesting ones. Hopefully. So just a quick background about Oxyco. So here at Oxyco, we design, develop and manufacture chemical surface treatments. We do that for a wide range of industries, some of which I'll touch on today, but predominantly we are a chemical company. We manufacture chemistry. We also do groundbreaking blue sky R&D, as well as product development as well. And manufacturing wise, we're vertically integrated. We not only formulate our products, but we also manufacture our key raw ingredients as well. In terms of our history, it goes all the way back till 1996, back at University of Oxford, when carbon research began there. Really, my involvement started in 2004 when I came down to the chemistry department to work as a postdoc. And everything from there on in is just kind of my life has flowed, and I've not really designed it much. We span out Oxford Advanced Surfaces in 2006. That was a spin-out company straight from the chemistry department. I moved over to that and left the university to become Chief Technology Officer. In 2007, we floated on the AIM stock market. That wasn't planned, and we got to a peak valuation of 150 million. In 2014, we delisted from the AIM stock market because it wasn't a great place to be with market crashes and everything else. It wasn't the best way for us to pull the company forward, so we actually took it off AIM and took it back to being a limited company. 2015, we switched to product development as a focus rather than trying to work with large companies and joint development. We actually decided to make our own products. And very quickly, we got traction in things like Formula One, some really exciting projects. From then, we've really just grown. We started scale manufacturing. We started getting real serious volume customers in places like Turkey. We then, 2021, 2022, started Oxyco Limited. This was because we saw this was the right time for us to expand as a company. We wanted to really grow, change the things we were doing. We started Oxyco to highlight that change in pathway and this expanding view we had of our markets. And we funded it by raising $10.5 million. Since then, we've grown the team threefold, and we've just entered into the Brazilian market, which is very exciting. That's a real snapshot of basically the last 20 years of my life. going to go over some of this now in a bit more detail, especially about surface functionalization. So this is an area of chemistry that you probably never will touch in your lives unless you end up working in it. It's fairly niche, and at its very basic goal, it's if you have a material and you want to change its properties for one reason or the other, how do you do it? If you've got a metal or a glass, or you've got ceramic, it's really easy to do. You can use everything from silanes, phosphonates, thiols. You can create self-assembled monolayers, really easy to change the properties. The reason for that is they've all got reactive surfaces. Metals, glasses, ceramics, they all have chemistry on the surface that you can bond to. You can form covalent bonds, you can form ionic bonds, you can have some type of bonding to them. You can quite easily come up with materials that have some sort of functional head, functional tail and reactive head, and you can get chemical functionality that way. The problem occurs is when you want to add chemical functionality to an inert polymer. And there's plenty of these around us. These can be thermoplastics, these can be thermoset materials. These can be the engineering polymers we see around us all the time. We use them because they have great properties. One of those properties is normally stability and inertness. We don't want materials we're out of plastic to swell with oils or change shape when they're in contact with things. That would be bad. The problem is this inertness means they're basically, they have no functionality at the surface. You can't use the traditional method you would use on metals. They just don't work. And it was this question that started off the research about, how do you modify plastics? How do you modify polymers chemically? How do you add functionality to them without creating a new polymer? And the answer to that is using carbines. So carbines are a type of highly reactive chemical intermediate. The one great thing about carbines is they do a whole host of reactions. They will pretty much react with anything that you have there. Carbines are the structure in the middle, very short-lived reactive intermediate, milliseconds, characterized by having 2 unpaired electrons on them. You can think of it as a diradical, but it's not, and they do very different reactions. The difference being carbines love doing insertion reactions. They love inserting into bonds. They can insert into oxygen hydrogen bonds. So if you've got alcohol, you can form an ether from that pretty easily. Yeah, not so exciting. One thing they can do really well, though, is they can insert into carbon hydrogen bonds. So you can actually form new carbon-carbon bonds by using carbons. That's really powerful. There's not many things that will do that. The reason carbines aren't used much in chemistry, and maybe a controversial statement, but they're not, is because of this reactivity. It's really hard to control what they're going to do. They'll pretty much react with anything that's there. There are certain reactions where that's not true, but generally they're pretty unselective. In the field of surface modification, that's exactly what we want. We don't want them to be selective. We want them to be able to put down on any plastic we have, or any polymer we have, and we want them to react with whatever they see. And that's exactly what they do. So what can we do with this? So I've got a few examples I'm going to go through of work we carried out in the university. The first one was colouring polymers. We wanted to be able to take polymer materials and show that they had some colour to them. You might wonder why. This wasn't for a printing application. This wasn't for any type of dyeing or anything else, because just modifying the surface, you don't get very much colour in there. It was for the simple fact we are a nanometer-sized coating that's organic going down on an organic substrate. It's really difficult to prove that you've actually functionalized anything. Nothing really to see. If you're trying to characterize it by analytical techniques, our coating pretty much looks like the substrate you're going down on. You're not really introducing anything functionality-wise that's new. Coloration is brilliant because the only analysis technique you need is your eyes. You can quite clearly see if you start with a polymer that's white and then you end up making it colored at the end, you've definitely done something, you've functionalized it in some way. This was the only reason we started doing this project, because it was a real quick and easy way of proving the concept. I'm not going to go into the synthesis, so don't worry if you're not an organic chemist, but just bear in mind for later bits of this presentation, it's really complex. There's a lot of steps here, and it's not particularly easy. What we were trying to do is a really classic bit of organic chemistry. We were going to do diazonium couplings. So what we wanted to achieve is functionalizing polymers with some type of tertiary amine, an aromatic tertiary amine, because we knew if we had that in there, we could react it with a diazonium salt and we could get a diazo coupling. Diazo dyes are brilliant, probably the simplest form of chemical functionalization we can do. Very reproducible chemistry, but it also doesn't work unless you have these type of aromatic tertiary amine compounds there. All the polymers we were modifying have nothing like that on them at all. So if you expose them to diazoniums, you see nothing. And pleasingly, it works. So we could take multiple different materials. I picked 3 out here because they produce the best pictures. So we have silica on the left. I will admit that silica is an organic polymer. We were expanding out to doing other things. Polystyrene and then polyethylene in the middle. And what we saw with this is that we could modify these surfaces. We could react them with different diazoniums. We could change the color on them. We could almost get a bit of a handle on how well they were modified as well by the depth of color we were getting. I didn't put some examples in here, but things like polypropylene and other materials like that. We weren't getting Teflon. We weren't getting great coloration on them, showing that we weren't getting as much modification as we were on these types of surfaces. But really, when we were starting out the group, it was a really quick and easy way to prove that this new chemistry that we developed was actually doing something without spending huge amounts of money on analysis and timing analysis as well. I cannot stress to you how difficult it is trying to find nanometer-sized layers on things that are organic. We've been through pretty much every analysis technique there is, and there's no good way of doing it. If anyone has any ideas, I'd love to hear them. Moving on from there, because coloration wasn't particularly interesting or worldly, we wanted to look at biocidal applications. So could we modify surfaces to include biocidal agents? Yeah, seemed pretty simple. There are loads of biocides known. It should be easy to just modify them in the same way that we did before. What we quickly found is that generally when we did that, we absolutely destroyed their activity. Good example is quaternary ammonium compounds, well-known biocidal agents. You have a quaternary ammonium head, you have a long tail, reacts with the cell wall, and the tail goes in and lyses the cell and splits it open. Brilliant. You tether them to a surface, you destroy that activity completely, because whichever way you do it, either the head or the tail can't interact anymore. So you take something that's really biologically active in solution, put it on a surface, it becomes completely inactive. So that approach was completely out the window. So we went back and thought about it, and we realized what we really wanted was a reversibly bound system. We wanted something where we could take a material, we could add something on there that was biocidal, but it wouldn't be permanently fixed. It would be able to go off and carry out its biocidal action in solution. But also we wanted to be able to put it back on there as well. So we wanted it to be reversible, because if we went off and reacted, then we'd end up with a surface not biocidal anymore. So we'd have to load it back on there. And preferably a really broad spectrum biocide. And that led us to this wondrous material down the bottom, which is urea hydrogen peroxide. It's a solid form of hydrogen peroxide, great for using in oxidations. And one of the key things about it is that the hydrogen bonding you get between the peroxide and the urea is really, really strong. And it doesn't get broken up by water. It's pretty stable to heat and light, and hangs on there. So our thought was, if we could hang the urea unit off like this, maybe we could load hydrogen peroxide onto the surface, keep that there as a biocide, It's not actually chemically bound, it's only hydrogen bonded, so it should be free to be released and move about. That was the thought. I apologize for the quality of this. I had to rip it from a paper just before I came out. It was an incredibly complex synthesis to make these urea materials. Really many, many steps to get there and very, very low yielding at the end. But we did it. And we can modify a whole range of things. So we modified everything from polystyrene to PTFE to cotton to PVC to tables to doorknobs to pretty much if I could find it in the lab and maintenance didn't stop me from taking it off, we took it off and modified it and you know, stuck it in hydrogen peroxide to see if it worked. And it did. We could take materials, we could hang off this type of urea on them. We could then dip them in hydrogen peroxide and we would load that onto the surface. We could test for that by a wonderful starch iodide titration. So we could just titrate the peroxide with sodium thiosulfate. We could use starch iodide as the indicator. So it's very visual and beautiful, having a deep purple color. And from that, we could look at how much peroxide was actually loaded onto the surface. So this was active oxidant we had loaded on. That's what we were measuring. The table on the far left shows you that we could load the peroxide on, we could titrate it off, we could then dunk it in peroxide again and wash it with water, and we could titrate it. And within the experimental error of us doing this by hand, we were pretty much getting the same loading each time we were doing this. And I think I got bored after 7 attempts because it wasn't changing at all. And there was only so much titration I could do as a postdoc before I got bored and wanted to move on to something different. We also looked at whether it changed over time. So we took samples and we left them out, just dry in the open atmosphere. And we found somewhere between sort of 72, 96 hours, we were starting to lose the peroxide off. We were starting to get a lowering of the concentration we had on there. Not exponentially, you know, it was only dropping a little bit. We hadn't dropped down by order of magnitude, but it was definitely starting to tail off. Not really surprising. We have an active oxygen species in the dry. It is going to tail off. This didn't bother us. The applications we had in mind for this would be where you were cleaning with peroxide, so you'd be constantly loading it back on anyway. That was the idea. And of course, the big thing was we could actually use it as a biocide. So we could take agar plates, we could put E. coli, we could put Staph aureus in there, we could create a little hole, and we could put polymers in, say polystyrene on its own, and modified polystyrene, and modified polystyrene with sodium peroxide. And pleasingly, the top two did nothing. The Staph aureus still lived and grew and did everything it wanted to do. But in the one that we had peroxide, we saw a zone of inhibition around it, indicating that the Staph aureus had died. Fantastic. So we had managed to load this biocidal agent on. Really interesting stuff at the time. So this was many years ago. I developed this when SARS and MRSA were a really big thing and C. diff in hospitals. And we thought this was going to be a really big product for the market, and it was going to be really exciting. And I'm going to come on to why I was completely wrong about that later on. Flipping back the other way, the other thing we could do, so killing stuff on surfaces is all great. Can we grow stuff on surfaces? So can we make things biocompatible? Why would you want to do that? Implants. If you have a plastic implant in your body, there's a good chance your body will reject it because it's plastic and it doesn't look like anything. Even if it doesn't reject it, you're not going to grow bone on it very easily because it's a pretty alien surface. What we wanted to do is look at whether we could improve bone growth over nylon implants, really, or plastic implants, but predominantly nylon. And the simplest way of us doing that is to hang something off that would bind calcium. Because if we could bind calcium down to the surface, we could kickstart bone growth from there and start growing stuff on. The simplest way of binding calcium down is to use phosphonic acids, and we came up with a rather elaborate synthesis again to come to a material where we could bond these phosphonic esters to a polymer surface, and then we could hydrolyze the ester back to the acid. One of the little eccentricities of carbene precursors is they're all acid sensitive. So you can't have a carbene precursor and an acid in the same molecule. You have to have them protected, which is somewhat of a problem, but there are ways around it using protective chemistry. So we could modify these materials. We could load calcium off the surface to them. And we could then look at whether they grew stuff. Now, this is quite a complicated picture, and this really is down to the fact that I wasn't very good at making samples at the time. What we can see here is on the left-hand side is day 3 and day 14 of us growing cell cultures on something called high bond N, which is just a nylon membrane. You can see after day 14, you get a pretty good coverage over that. And when we count stuff up, we're about this level here, about 3,000. If you look at the 2 treatment membranes we've got, 7A and 8A, it doesn't look like actually we've improved the cell growth very much at all. Pretty much the same level after 14 days. In fact, arguably a lot less in the intervening time periods. The thing you need to look at is the pictures. Unfortunately, one of the issues with high bond N is it's not particularly stable to acid. So during my hydrolysis of the phosphonic ester to the phosphonic acid, I actually destroyed half the membrane, if not more than half. So while the numbers are the same, actually we're growing the cells on far less actual membrane. We have far less surface area there on the ones we treated compared to the black material. So if you account for that, it's actually a massive improvement in the amount of cells we're growing. It really does improve the biocompatibility of these materials by a massive amount. The other thing that was quite fun to look at was wetting, so changing the way the liquids behave with surface. This has lots of practical applications. Unlike a lot of the other things that sound great, this actually has a lot of practical applications. We do a lot of this currently in the company as well. But I thought I'd throw this slide in because it really kind of emphasizes what you can do in carbene chemistry and why it's so useful. What we have on the left is the water contact angle of 2 materials. If you're not familiar with contact angle measurements, you are very simply taking a substrate and you're putting a known volume of liquid, you're dropping onto the surface, and then you're just measuring the angle. It's good, you can see that here. You're measuring the angle of the water droplet with the surface. A really high water contact angle means you are not wetting. A really low water contact angle means you are wetting and you like the surface. So we have 2 materials. We have Teflon at the top and a silicon wafer at the bottom. You can't really get more polar opposites than sort of PTFE Teflon on one side, which is highly fluorinated, really hydrophobic, and a silicon wafer that's been cleaned, which is fairly hydrophilic. And you can see that from the contact angles going from 110 to 30 in the 2 materials. What we can do though, is we can take one carbene surface treatment and we can apply it to both materials. And because it's a carbene, it's going to react with PTFE and it's going to react with silicon because carbenes react with everything. And what we end up doing is we end up homogenizing those surface properties. So instead of having 2 things that had very polar opposite wetting properties, we can make them look exactly the same now to water. Silicon at the bottom, PTFE at the top, water contact angles now 70 in both of them. Same surface treatment. While that doesn't sound particularly interesting, it has a lot of uses in industrial applications where you might be making electronic devices, you might be making electronic structures where you have different materials present at the surface. And if you need to print onto those, or if you need to get materials to flow through, such as in a flow cell, you don't necessarily want different wetting properties, especially in something like a flow cell. You don't want the liquid to potentially move in different ways. So using this technology, we can even out properties across different materials that are really quite alien to each other. This pretty much forms the basis of everything we do. This changing properties to make them more useful and make materials more compatible with one another. The last example I'll go over is functionalizing polymers because we could grant money for it. Honestly, I didn't really have an answer to this. This was where we were modifying diamonds. Unfortunately, I got really excited by this project when I found out I was modifying diamonds, and then they all turned up. And if anyone's worked with synthetic diamond, they're all just black powders. None of them look like this. So it's really quite, anticlimactic when you get them. What we were looking at is, can we modify diamond surfaces? You can't, okay, PTFE you would normally think of as being quite inert, but diamond you would normally think of as being an inert material. Carbons, again, can easily modify it, no problem at all. Carbon hydrogen bonds at the surface, we can react with those. There's basically no difference between polyethylene and a diamond surface to a carbene. It's happy to react with both. Very simply, what we wanted to do is introduce chemistry onto the surface of diamond that isn't there normally, and then just use X-ray photon electron spectroscopy, so XPS, to see if we can see it. Simplest thing you could find was iodine. Stick a nice heavy element on there that is not naturally occurring on diamond, and XPS it, and it comes out really clean, see it really easily. The reason you use iodine and not chlorine is because if you touch it, you get chlorine on there from salt, so you definitely don't use that. And bromine is a real pain. Iodine's the way forward, because you just don't naturally find it occurring in samples. This was great, really interesting stuff. Had a load of fun on the project. Pointless in terms of actual use, but again, it confirms this fact that carbenes is just this brilliant thing of modifying anything you want. That is what I was doing in university. Now I'm going to move on to the real world of where we then move beyond the university. We span the company out and the challenges and everything we found from that point onwards. So the first thing you need to do if you're going to form a spin-out company, or if you're going to spin out any invention, is protect your invention. I'm not going to go over this in any detail because I do talks on this that are an hour in its own right, and also it's quite boring. But there are basically 4 ways of protecting your inventions, and they are patents, copyrights, trademarks, and know-how. I'm pretty sure everyone here is familiar with patents. I will guess not many of you actually know what patents do, and I'd be interested post-talk if anyone wants to tell me what they think a patent allows you to do. Good discussion, because most people don't have the right impression of that. But the reason I bring this up is, if you do ever have an invention that you think you might want to commercialize, you might want to spin out, you need to think about all these things really early on, especially before you start disclosing them to anyone, because then it's too late. But the things that you should be familiar with, there are strategies you need to be putting in place before you can start commercializing inventions, because otherwise you will lose everything. Because of all 4 of these facts, there are lots of things I can't talk about, unfortunately, about what Oxeco currently does. It's the other reason I threw the slide in. There are a lot of things I'm going to have to talk around. There's some discussions we might not be able to have just because it's either taken up by trademark, but more importantly by know-how, which is, if you don't know, know-how is inventions you have, you just don't tell anyone about. It's things you keep internally in the company. It's the most secure, cheapest way of doing something. You just don't tell anyone how you're doing something. But that's my caveat from being a bit evasive later on if you ask me anything. Right, so pitfalls of commercializing university research. If you are in a university and you are doing R&D, you have a defined project and an end goal that you're probably really familiar with. If you're doing any type of end of year project, or PhD or anything else, you will kind of know where you're trying to get to at the end, and you'll have some type of scheme to get there. You'll also have access to a load of equipment, pretty much anything that you need within the university. As well as that, you'll have access to collaboration. So all of those projects I spoke about before, the coloration, the biocidal, biocompatible, the diamond modification, even the wetting, I didn't do them all on my own. I worked with pretty much loads of different departments from Oxford to get all that stuff done. I know nothing about doing bioassays or biocompatibility or XPS. I just worked with the relevant departments then. It was great. You have a beautiful organization for collaboration, you can do that. You also have, I guess with the collaboration, you also have access to a load of really talented people with experience that if you're stuck on stuff, you can bounce ideas off. And because of that, you're in a really problem-solving environment. University R&D, you're used to stuff not working. You have people you can talk to and experts in that area, world-leading experts in that area that you can talk to about it. Going to a spin-out research. You have absolutely none of those things I've just discussed. And on top of that, you have a host of other problems to deal with. You've got 0 levels of scale-up know-how. I can pretty much guarantee that anyone that is commercializing university research that's coming out of chemistry doesn't know how to scale up to begin with. And I might be, not too broad, but most people won't know how to scale up because we just don't do it. We scale to a certain point in labs, but we don't go any beyond that. You have very limited manufacturing expertise. You might have made things once or twice, but have you made them repeatedly? Have you thought about all the issues that comes with supply chain and being able to produce stuff for quality standards? I mean, you'll learn very quickly, but you won't have experience of it. You probably won't know the needs from the end market, the form, the function of the cost. You'll have a great idea, but you probably won't know what the market actually wants. You've got to work out how you're going to commercialize it. That's an entirely separate, very long discussion, but most people don't actually know what they have. They know they have technology, but they don't know what the product is and how they should commercialize it from that point. And just because you have great tech does not mean you have a great product. And I will go on a small rant here about carbon nanotubes and graphene. So anyone in the audience hasn't heard of graphene would be an easier question to ask. Right, no hands up. Graphene is the amazing wonder material. It's going to solve all our problems. We've, as a country and as a government, we have spent lots of money in graphene research. Anyone know any graphene products that are out in the market today?
Tennis racket.
Tennis racket, yeah, it's a fishing rod as well. Anyone else?
Allegedly for carbon nanotubes batteries, but it's know-how, so they don't.
No, yeah, that's true. Yeah, and you can use graphene batteries as well, but yeah. But arguably not so much, carbon black still pretty good in batteries. So two great examples. I don't think everyone, when graphene was going to be the next wonder material, was expecting it to be used in a tennis racket, a fishing rod, and actually in cement as well. Not canon. My point is, there's a lot of hype that goes into stuff sometimes, and you can get lost in that. And especially if you develop something, you can get really lost in how big you think your invention is going to be. And you need to take a step back and really logically look at things about whether you're right or wrong. No, that's not me. That's me. Two computers confuse me. There's so many differences. This takes like 2 slides. You've got to build a team. In university, you don't need to do that. Your professor or principal will do that. If you're starting to spin out, you actually have to build a team from scratch, which is really complicated. And managing people is really complicated, especially if you've never done it before. There's a big culture shock because you have no safety net anymore. If you're leading it, you are leading it. And if anything goes wrong, you're going to be held accountable for it. And there is really no one you can fall back on. It's all on you. You'll find lots of experts in areas that actually aren't experts. We get this a lot, both with consultants and with customers who you think are an expert in their field. And you realize they are an expert in their fields, but just not the bit that you're working in. And that bit they know nothing about. So you've really got to know when to listen to people and take their advice and when not to. And that's quite difficult when you're starting out because you don't have that confidence. Everything takes longer than you think. It's just everything. Whatever you're trying to do, it will take longer than you think. And you suddenly have a load of stakeholders you've never had before. You will have investors most probably because someone's giving you money unless you are exceptionally wealthy and you funded it yourself, which trust me, in chemistry, you're going to need a lot of money. you're going to have customers somewhere. You're presumably selling something to someone. So you're going to have customers as a stakeholder, and you're going to have staff. And all these people are going to be looking to you and holding you accountable for different things. And you need to be able to manage that. None of these things you have to remotely touch in the investor. These are all new things that suddenly hit you when you start spinning out companies. You've really got to understand your market fully. You need to understand the wants and needs of the end customer. Good example of this, the biocidal product I talked about earlier on. I thought that was great. I mean, I developed it, so yeah, maybe I'm a bit biased, but I thought it was fantastic. When we first started OES, we went out to the US, we went out to loads of places to try and sell it. US being the main one because they're really hot on medical stuff and disinfection. It was a real thing. We went around two main things, looking at hospitals for cleaning surfaces and looking at water purification. And we got knocked back by everyone for two totally different reasons. In hospitals, we were told there isn't a problem. And in fact, there isn't a problem. You don't need biocidal surfaces in hospitals because they have really good biocides already. It's just they're not used properly. There is no guarantee that us creating a surface that would bind peroxide, people just still wouldn't use the cleaning agents properly. It would be no better than what's currently available. So they knocked us back for that. They also knocked us back for the same reason that the water filtration guys knocked us back for. We use peroxide because it is pretty harmless, really, environmentally. Yeah, okay, it's obviously an oxidant, but you can gargle with hydrogen peroxide if you so wish, 3%. But it's also odorless and it's tasteless. And we thought they were great things for water purification and for cleaning. Turns out, totally the opposite. People don't want cleaning agents that are odorless and tasteless because they don't know they're cleaning. All the US, all they wanted was chlorinated stuff because when you clean the bleach, it smells like bleach. So you know it's clean. They wanted water purification tablets and water filters that gave you a kind of chlorine taste to them because you knew your water had been purified. They didn't want something that tasted of nothing. We didn't understand the needs and wants of the customer until we went out there. We developed technology that we thought was great, and then we went out and tried to sell it, and it turns out it was the complete opposite of what people wanted. That's a real danger with early stage research, is you develop stuff without looking at what the customer actually wants and needs. You develop a technology, you don't develop a product. It's a bad way of doing stuff. The second one is timing, competitive development. I'm going to talk to you about Project K because it's a really interesting one, and one very close to my heart. So, the first rule of when you start your own projects is any new project you have has to have some really cool acronym as its name. So we had, I didn't name this one, so it's not a very cool acronym, but we had KP, which was Controlled Adhesion of Insulators and Printed Electronics. You ignore the O and the I because otherwise it's really weird as an acronym. We were looking at creating these things, which are flexible displays, preferably full color video flexible displays. This is a picture from Sony from way back in the early 2000s. We were looking at rollable flexible displays. We weren't looking at the front plane, that was different technology. We were looking at the OTFT at the back, the driver for it. If anyone's unfamiliar with these, it's basically where you have organic semiconductor, insulator, plastic substrate. We were looking at flexible, so it must be plastic. In the one we were looking at, we had PEN substrate, which is formed of polyester, and a PTFE coating on top of it called Teflon AF. Teflon AF sticks to nothing at all. It doesn't stick to anything. The issue that they had was on a glass substrate, it's fine. You put the PTFE down, nothing has to happen. In an OTFT, it's flexible, everything rolls. Because there's no adhesion, as soon as it rolls through, everything delaminates, it comes away, and it doesn't work as a TFT. So they needed to improve the adhesion between those two layers. But how? Normally, we were used to dealing with inert substrates. Here we had an inert substrate and an even more inert coating going down on top. This led us to innovate. This led us to the breakthrough, which actually formed the company going forward and has been the focus of us going, we're successful where we are now, which is where we had to develop new chemistry. The chemistry we had before just wouldn't work. We couldn't functionalize it and hang something off. Teflon doesn't like anything. So we decided, well, what's better than having one carbene is having loads of carbenes. So we created a polymer that had lots of different carbene reactive head groups on it. And our idea was, if we create a sandwich between PN and this Teflon PTFE layer with our carbenes in between, we sandwiched them together and cured them, we should be able to react in all 3 dimensions and cross-link everything together in one gigantic loop. And you can. This is optical microscopy of a Teflon layer. This is the PN substrate, and this is where we've scratched down. This was actually supposed to be a test called a crosshatch tape test, which is widely used in coatings. You scratch through, you put tape down on top, you rip it off, and you count how many squares come off. You can't do it on this because it's PTFE, like none of the tape sticks to it. So that caused some issues. But pleasingly, there is so little adhesion that even when you cut through it, on the untreated, everything just delaminates away and pushes away. On the treated one, we see no delamination. We're actually holding these layers together. Nothing delaminates away. That's a bit basic. We can be a bit more exciting than that, a bit more scientific. We can use nano indentation. So here we just use nano indenter, poke it in the surface and drag it across. We measure the force. Quite clearly, what you can see from all of these is you get gross delamination away. As soon as you hit, you're basically just ripping this Teflon off. There is no adhesion between these two things. Again, in the treated one, no delamination. You can jam the nano indenter in, you can drag it across the surface, nothing comes off. As a chemist, this is all really interesting for me when we were doing this project. These were all techniques and analysis techniques I had no familiarity with before. The great thing about working in this field is you get to learn about a whole host of different materials and materials testing that just as a chemist, you don't normally get any experience. And the last one we did was pendulum impact using a nano indenter. So instead of dragging it across, you just jam it into the surface really hard. And what we can see here is what we call the halo of delamination. So when you jam it in, you basically see this little halo appear around it where it's delaminating. And in ours, you can. So brilliant. So we can bond these materials together. Prove that lots of different ways. We show that they're solvent resistant, they can do everything else. Crucially, we show that they don't affect mobility. So we could make this into a transistor device. We could put semiconductor down the top of it. We could put source and drains on there. And we could create an OTFT that worked. And there was no detrimental effect to having our layer in there sandwiching and holding everything together. So absolutely fantastic. For us, a massive win. So the end market we were looking at for this at the time wasn't for, well, we were aiming for full flexible color video. That was going to be way, way off. So we were going to accept flexible e-paper to begin with. So this was going to be rollable books, newspapers that you could just, pull out a screen and have it there in your hands. We were doing this back in 2007 at this point. You'll notice a lack of full color or even flexible e-papers that we all have at the minute. And there was a reason for that. And if anyone knows what it is before I go into the next slide, please shout out now. What killed this project? No, not your phone. Something worse than your phone. I would say anyone knows what that is, but it's actually written on it. So the Amazon Kindle came out in November 2007. Kindles are not flexible at all. They've got glass in. They have none of the benefits that they're not full color video either. They have none of the benefits of the technology we were developing with OTFTs. What they were, though, is first to the market, and they were really well received by the market. Kindle managed to basically destroy the flexible displays market for a lot of years. Stopped it dead in its tracks just because they got to market first. This wasn't planned. Our part of the project, what we were developing on, all worked really well. But it's just a good example of how you've got to be careful when developing new technology, because it's not just your technology risks you have, you've got to think about the external environment and what everyone else is doing as well that can really scupper you. The bonus to this, though, is the technology developed for Kate actually went on to be the bread and butter of what we use now. So actually, we wouldn't be here without this. So for the final part, I'm going to talk about where we are today. And I've just basically called this establishing your niche. We have something called Onto, which is what we call our technology platform for carbines. We call it our chemistry engine. And for us, it sits at the heart of science, technology, engineering, chemistry, material science, and nanotechnology. These are all disciplines that we deal with on a day-to-day basis. My team are pretty much all chemists, but we're not just chemists. We're chemists by training, but we're all material scientists now. We're kind of all engineers because we've had to pick it up, and all the people we talk to are engineers. So we have to kind of learn that language as well. We sit at the interface of all these things, and it's really fun and exciting, also challenging. We found the place where we could sit best is in adhesion, is bonding. A bit like the Cape project, we found adhesion phenomena the best things that we can look at. There are loads, well, actually there are 5 different ways you can make stuff stick together. You can do really weak van der Waals dipole-dipole interactions, which we're not going to bother talking about because engineering-wise they're rubbish. You can do ionic bonding, great, we're on plastics, there is no charge. You can do mechanical interlocking, which is sanding, that's pretty boring, and I'm going to disparage that quite a lot in a minute. Or you can do covalent bonding. Entanglement is a bit of a weird one. You can't really do that on the polymers we're talking about. But you can do chemical covalent bonding. We can bond between materials and make them stick together. And we found that's what we're really good at doing. And also, loads of people want to do it. We found our niche. Too fast. So, we have 2 product families that stem from the Onto chemistry engine. We have Coke-Fast and we have Semperbond. Can't tell you how long it took us to come up with those names, but a lot cheaper than hiring someone to do it for you. If you want to see how much that costs, yeah, try hiring someone to come up with branding for you. Coke-Fast is for improve the adhesion of paints and lacquers to materials, and Semperbond is for bonding. Why do you need to use Coke-Fast? Well, at the minute, if you are making a part and you want to paint it, and here we have a lovely bit of carbon fiber epoxy. So this is carbon fiber weave with epoxy over it. So it's composite material. Most of the stuff we do is on composite materials, and mainly because of the end use of them. Before painting, you tend to sand the material to get adhesion to it. So when I went back to that slide before, that's mechanical interlocking. You're rubbing the surface, you're roughening it up to create things that when you put a coat down in, it can sit inside and it doesn't pull out from that. I can't tell you how bad abrasion is. If anyone's done any sanding of anything ever, it's horrible. It's really dusty. It's really time consuming. It hurts after a while. Also, you can damage the substrate. Like this is us doing it. You can see here, this bit, well, you might not be able to see there, but that bit of weave doesn't look the same. That's because we've sanded too far and we've actually damaged the weave underneath. No one likes adhesion. No one likes sanding. In fact, in the 15 years of me talking to people about this, only one person has told me that they don't mind sanding, and I think they just didn't want to talk to me anymore at a conference. Otherwise, everyone else has said they hate it. Why do we do it, or what do we work on? Our main applications are in the transportation industry. This is where people are replacing metal parts with composite parts for lightweighting. In the transportation industry, they did this a long time ago. It's to improve fuel economy and reduce costs. So you replace metal with what we have here, which is polyester with glass fiber. So glass fiber SFC, basically. The key thing you can see from both of these pictures is these parts we're dealing with, like here, none of them are flat. Sanding a table is really easily because it's a nice flat. You can just go over it really quick. When you've got things that have got ridges and bends and everything else, it becomes really difficult to sand it fast. That's where coat fast can come in. We can remove that sanding process completely. We're a spray applied coating. So if you can spray a paint there, you can spray our product there. Remove the sanding completely from the application. We've got a success story here with a company in Turkey called Polkema. We've been dealing with them for ages. Since 2019, we've been supplying to them. Their challenge was they were growing their department. They were going to make more parts, but they were sanding. And if they wanted to double the amount of parts they made, they had to double the amount of sanding they did because it's a manual process. You can't have one person sand more than one thing. So they needed double the amount of people and then double the amount of space as well, which just wasn't economical for them. So they looked at using our Coatfast product, and I can say it went very well. They improved their capacity by 10 times. They reduced the time it takes to prepare a part by 90%, and they reduced the amount of people they needed for surface preparation from 8 people down to 1. So that meant they could easily double up the size of their production and actually deploy those people they had sanding doing more valuable things parts of the factory. Fantastic. It's been a really good market for us. As I said, we're now expanding out from Turkey into Brazil, which is really cool and exciting as well. Key thing about this is it raises some challenges, especially mindset-wise. It's how do you keep customers happy? Supplying people in the transportation industry is very difficult. They have criteria they have to meet in terms of quality. They have timescales they have to meet, and they cannot be late. So if you're going to supply products into them, you have to make sure that everything you deliver to them is on time and it's exactly to spec. And that is something that if you're going to start manufacturing, you have to be pretty good at pretty fast. Otherwise, you're going to get sued. Where's next for the Coatfast product? Well as doing the front of trucks, these things are also sanded. So that's a wind turbine. I think it's really small. That's only an 80-meter long wind turbine. These things are molded in 2 halves. See the joint down the middle, and they glue them together. And then you have a team of about 12 people that walk up and down them and sand them by hand and sweep the sand off. And there's someone at the bottom sweeps it up into a pile and hooves it up. And then they flip the blade the other way and they do the same on the other side. It takes ages. We're looking at, can we replace that entire process with our Coatfast spray applied material? So it makes it all quicker, faster, healthier. It's really what we're trying to do. Our goal is to come up with environmental solutions. We're a very green, low-tech company, green, zero emissions company. We're trying to work in areas in clean energy generation and improving the environment. So anything like this is perfect for us. Second application, I'm going to talk about Semperbond. That was about bonding. Anyone ski? Anyone do cross-country skiing? Basically, cross-country skiing is a real pain because you have to drive your skis on the back. It'd be really great if you could find a way of not doing that. We were working with a company called Elan designed a cross-country ski that folds up on itself. However, they had an issue. Generally, skis have a wood core to them. They couldn't use wood. The aluminium plate on top was too much. So they were going to use a glass reinforced thermoplastic instead. However, the issue they had is when they made this stack up, there was no adhesion between layers anymore because they'd suddenly moved from a wood material that bonded really well to everything to a plastic that didn't. They came to us. We developed a treatment for them. They can assemble these things together. They would twist, they would twist, they would flex, they would hold together during the rigors of skiing. And what that allowed them to do is make the world's first folding ski, which is pretty cool. It literally looked like this when it was unfolded, and like that when it was folded. So you could have it in both sides of your backpack, really quick and easy. Ironically, most of these were sold to various militaries around the world for military skiing rather than commercial skiing. I guess because they do more cross-country. But it's a really fun, exciting application of chemistry. And I can't tell you how exciting it is to see something that you've spent years developing as a technology be formed into a product and then go into something in real life and you actually see it there in front of you. It's a really nice feeling. The other one we do a lot of is Formula One. It's great watching Formula One cars go around knowing that I hold bits of that car together. It's a really good feeling to have, knowing that you've developed something that's actually used in the real world. The last thing I want to touch on, or the second last thing I want to touch on, is manufacturing. There are a lot of challenges, as you would imagine, with scaling up university research, going into manufacturing. The main one is, how do you go from working in a fume hood to working in things like 800-litre vessels? The thing is, it's not a massive jump. You can't be bringing chemical engineers in for this, because generally they're working at a scale that's way above this. This is somehow an irritating scale that's too big for you to do as a chemist, but way too small for a chemical engineer to really want anything to do with. So you have to learn yourself, and you have to come up with ways of doing it. The key thing about manufacturing, and I've touched upon it a few times, it's about quality and it's about delivery. And it's about having processes in place. So we're an ISO 9001 certified company. We have a quality system in place because we have to. Our customers wouldn't use us otherwise. We have to make sure that everything we make is the same every time, and it goes out on time. I mentioned before, we're vertically integrated. We manufacture all of our key raw ingredients ourselves, and we formulate everything ourselves, and we supply from Oxford. We are looking at growing all of our facilities at the minute, so we need way more lab space and also way more people in the future. So it's a really exciting time for the company as a whole. And that brings me finally on to what is Oxeco's future. And I've left this slide vaguely blank because I can't really talk about much about it because of confidentiality. But suffice to say, we're up to loads of exciting things in the R&D space. As well as expanding into new territories commercially and improving our manufacturing and growing our team, we're looking at really innovative projects in battery spaces, so lithium-ion batteries. Where can we apply surface chemistry and surface modification in lithium-ion batteries? We're looking at the hydrogen economy. What can we do in things like hydrogen storage? Hydrogen tanks, for instance, are a laminate of materials that are all have to work together. Sounds like a perfect place to be using adhesion promoters to make sure nothing falls apart. Fuel cells, electrolyzers, for generation of hydrogen or use of hydrogen. Again, all multi-component systems that have to work together. There are a whole host of applications when it comes to surface treatment where you find where surface properties are really important, and we're looking at them. If it's something to do with zero emissions, if it's something to do with decarbonisation, it's of interest to us as a company at the minute. And surfaces as well, obviously, because that's what we do. But that's it from me. If you've got any questions, it'd be lovely to hear them. But really what I wanted to get across in this is spinning out a company is really fun. It's really difficult, but it's also really fun. Chemistry is really powerful. It can take you loads of different places, especially places you never thought you would get to. And you can meet lots of really interesting people that aren't chemists. So yeah, thank you all for listening, and yeah, any questions I'd love to hear. On time.
Do we have any questions for Dr. Griffiths today?
Yeah. I'm interested in what you actually manufacture, because different clients will be making things of different shapes, sizes, and materials, but they want then to be able to put surface coating on, say, you're dealing with a pretty nasty chemistry, and to what extent are you providing the mechanism for their workers to be able to safely do it? You're not painting it on, you've got to provide something rather more.
No, we are actually. No. So one of the things we are just painting it on. One of the things we pride ourselves on is we don't need to use specialist coating equipment to apply our treatments. the first application we ever had in Formula One, one of the things they wanted to be able to do is apply it in a pit lane. So we had to come up with a way that they could apply our chemistry just using a brush, mixing by hand, by just shaking, applying with the brush, and then curing with a heat gun. So simple application as we could possibly get away with. I won't go into it. There's a lot of things we spent early in the company looking at how we make carbine safe to use, and yeah, that was a challenge. But actually, if you look at it now, we are way safer in a health and safety environment than a lot of the paints that are used. So most paints that are used are isocyanate based. They all have a lot of aromatic hydrocarbon solvents in. From a H&S perspective, we are way safer than those. But yeah, that was a good 10 years of work getting to that point.
Any more questions?
Yeah, the biocide application.
Yeah.
You didn't find an out before.
Yeah.
Has anyone looked at the food industry application?
It's an entire story in its own right. Yeah, so food is really difficult to get into if you want food contact approval, just because everything we're doing is novel chemistry, and the costs for doing the food contact testing and everything else is pretty big. Showing you don't leach off the surface at all is quite a difficult thing and a very expensive thing. So it's something we commercially we're not looking into, no.
Well, potentially huge markets. So
Yeah.
I think things like application of conveyor belts and things like that.
Yeah. There's
The big issue.
it's interesting when you look at it's something we looked at. Sometimes you can have quite large markets, but there's just there's a lot of volume, but no real money there. So the markets we're talking about in a minute, where we currently sell Coke Fast and Semperon, then they're very valuable, but not necessarily very high volume. But that's great if you're in terms of manufacturing, you don't need to make lots of things. One of the original things we had a problem with when we started is the main applications for surface chemistry and polymers was in disposable packaging. So we had loads of applications to begin with where people wanted us to modify disposable packaging, but they needed us to do it really cheaply, sort of less than half a euro cent per meter squared. But also you needed to be able to produce 10 tons of it to get it into initial application. So you had this challenge that you were doing stuff in the lab at a really small scale, and you knew if that went right, you then had to jump to 10 tons. So yeah, we picked our applications carefully based on size and also value. Yeah.
The other thing, I might have missed it, but the Coke Fast.
Yeah.
Was really good. Is that the paint itself, or is it like a primer?
It's just I'm going to be careful. So it's not. It's a primer. So it's a surface treatment. So it just removes the need for sanding. So just paint it as you would normally. Yeah.
Yeah, it's an interesting balance on the sort of cleanliness side, because sanding is a really messy business with huge health concerns.
Yeah.
For the operators and the environment. So I think actually yours is probably a huge step.
Absolutely. Yeah. No, sanding is a terrible process. You've not just got sanding issues, you've also got the vibration issues as well. So that's not great. Having constant vibration for workers isn't fantastic. So yeah.
There's great concern about wear on tyres running off into the runoff water from motorways and so on. Do you have to think about the end of life?
So yes, we do. Yes, in all of our automotive applications, we absolutely do. The one bonus we have is that our layers are somewhat maximum 1 or 2 microns thick. So actually, when you start doing end of life assessment, we are negligible. A paint layer is 20 to 50 microns. We are 1. So yeah, we don't really form part of that. But yeah, it's something we have to go through the process for.
Julian, did you have?
I might have misunderstood or misheard some of the in the earlier part. When you were talking about work with colour, those compounds or maybe intermediates look like azo dyes.
They were.
But I thought azo dyes were unstable, and that's why they've lost favour in the textiles.
Oh, they absolutely are. Yeah, they're UV unstable. They flip. they flip between cis and trans when you expose them to UV, and so that sometimes makes them coloured or colourless. Yeah, no, so the coloration literally was just a way of us quickly visualising that we've modified materials. Commercially, you can't get very much down to the colour, the actual depth of colour is tiny. So you would never use it for printing or anything else. It just wouldn't give you enough thing. Literally just for proof of concepts more than anything else. Using a chemistry that's so old that everyone knows that it works really well. So yeah.
Could you have another round of applause for one,
And on trains, peers and other.